the lecture of today. Well, all the previous examples that we have seen, the linear model, the linear regression model, the logistic regression model, the Poisson regression model, they can be all embraced, embedded into a completely unified and general framework. We call that generalized linear models. Now, if you go back to all these previous examples, to the linear regression, logistic regression, Poisson regression, you will see that we follow some kind of pattern to construct this model, some kind of general strategy. Essentially, we constructed these models in two different steps. We define first, or model first, what we call the systematic part of the model, and in a second step, we define and model what we call the distribution part of the model. And this can be done in each of these, and actually we did it in each of these previous models, linear, logistic, Poisson. Now, what is the systematic part of the model? As the name says, is when you try to reflect the effect, the systematic effect of certain covariates on the average response. So essentially, the systematic part of the model is a model that we state to describe the average, the mean structure. And then what is the distribution part of the model? Well, there we describe how the observations vary around this mean. We know that not all observations in a random process are exactly equal to the mean. So we first model the mean, that's the systematic part, and later we need to state a distribution to explain the variation of these observations around the mean. And we call, essentially, that is what we are going to do today, but now in a completely general fashion. And this is what we call generalized linear models. Why linear? Well, these models are non-linear models in general, but they are based on a linear predictor. So you model the mean using a linear predictor of your covariance. Now, this class of model, the GLM class, has played a very important role in the development of a statistical model in general. And it has allowed to also to create a unified approach for fitting and making inference across all these different types of models. So let's do it. The systematic part. What we do in the systematic part, we try to model the average response. So you have your random variable y, and this y can now be completely general, can be binary, can be continuous. We're going to see later some restrictions on it. And we try to model the mean response using a set of linear predictors. We call that eta. From there comes the word generalized linear, because we are still working with a linear predictor, even though the model as such is non-linear. And how we model the mean? Well, you can do it in two different ways. You can use what we call a response function, or you can use what we call a link function. And one is the inverse of the other. So it's two different ways of expressing the same thing. The response function is what you use when you want to link the mean to the linear predictor eta. The link function is what you use when you want to link the linear predictor to the mean. Guys, this is two different ways of saying the same thing, essentially. They are completely equivalent. So if you express mu, the mean, as a function of the linear predictor, that function becomes the response function. If you express the linear predictor as a function of the mean, that function over here is called the link function. And that's pretty much it. The only thing you need to take into account is that when you use a response function, or equivalently a link function, you need to make sure that you get valid values for the mean. Because, for instance, if we are dealing with binary outcomes, then we know that the mean is a probability. So you need to make sure that this side over here has or produces valid values of a probability. It needs to be between 0 and 1. If you are, for instance, dealing with a Poisson stochastic process, then this mu has to be positive because it's the average of counts. And then you have to make sure that this response function guarantees that the right side of this equation stays positive. So you need to be careful when construct or when you define a response function or equivalently a link function, you need to make sure that you get valid values for your mean. But that is the systematic part. You just use a response function, and when you use your response function, you link your mean mu, the mean response, you link it to the set of linear predictors in this way. Or in a completely general fashion, you transform your mean using a link function g, and now you use that to link it to the linear predictors. But these are just two different ways of stating the same, if you want. Fine, we have the systematic part. What about the distribution part? Well, now we have a mean, we have modeled the mean, we have here our model for the systematic part, but now we need to describe how the response y over here is going to vary around the mean. And to do that, we need to now set a probabilistic model that will explain how y is going to move around the mean. And we have seen different models. We saw, for instance, the normal model. That's what you do in linear regression. Or we saw, for instance, the binomial or Bernoulli distribution. That's what we used when we were dealing with binary or binomial data. Or we use the Poisson distribution. That's what we used when we were dealing with count data. Now we are going to introduce a general family of distributions that will encompass all these other previous particular cases, the normal, the Bernoulli, the binomial, the Poisson. They are all special cases of this general family of distribution. And we call that family the univariate exponential family. And it's just a distribution. It's just a general distribution that encompasses all the previous one. And here you have the expression for a univariate exponential family. What we call it univariate because it depends on a single parameter, a univariate parameter here, theta. You may also write a multivariate exponential family. In that case, theta will be a vector of parameters. But we are going in GLM to deal basically with a univariate exponential family. And this just, as you can see, it depends on the exponential here. We have an exponent here, and this is the expression of the univariate exponential family. It's just a formula that will give you a family of distributions. Okay, let us study this family of distribution a little bit more in detail. What is theta? As I told you, this is the parameter that characterizes the distribution. You have, in order, for instance, in the normal distribution, you have two parameters. You have the mu and you have sigma. In the binomial or the Bernoulli, you have the pi. Here, we consider theta the parameter of the distribution. We call it, in this case, a natural or canonical parameter. Now, if you look at this word, something you should hear a bell in your head, because when we were talking about the link function, we said, for instance, that the logistic link was the canonical link. You remember? Or we said, for instance, that the logarithm link was the canonical link for the Poisson regression. And now we call this parameter the canonical parameter. Does it have something to do with the canonical link? Yes, it does. And we will see that shortly. But let's, for the moment, forget about that, the relationship between the canonical parameter and the canonical link. We are going to see that later. And theta is just the parameter of the exponential, the univariate exponential family, and we call it the canonical parameter. More about that in a few slides. What is this B function over here? Well, it's a very important function when you're dealing with the exponential family. So here you have the canonical parameter, we call it theta, and now you have in this formula, in this expression, a function of theta that we call it B of theta. And it's a very important element in the distribution. It's a function, basically B of theta, that guarantees that this is a density. And what I mean by that, it guarantees that you can normalize this density. And what that means, normalize, means that beta is such that the integral of the f of y, the f of y is always so difficult to represent, the f of y, given theta, that integral, you know that if we are dealing with a density, that integral in y, put here d of y, that integral has to be equal to 1. Is the analogous formula to say that if you have a set of probabilities, they all have to, the probability of exclusive events, they all have to sum up to 1. Well, it's the same. So it's just a function such as we can normalize the density. That when you calculate the integral, it is equal to 1. And we will ask a couple of more properties for this b. It has first and second derivatives. So you can calculate the first derivative of b with respect to theta, and you can also calculate the second derivative of b with respect to theta. So theta, the canonical parameter, and this b of theta over here is a function that allows us to normalize the density and has the first two derivatives. Now you have this other element over here, which is a function that depends on two things, depends on psi and depends on w. Usually, you choose this A as the ratio between psi and W. And psi is called a dispersion parameters. We will learn a little bit more about that later. Psi is called the dispersion parameter, and W is just a known weight. But here we leave it in a more general way. So in principle, this A of size and W can be completely general function. But keep in mind that most of the time we will use just psi divided by W. That's just a constant there, doesn't depend on y. And then you have this other function over here. I think that we can go to the next page. That is just a general function that doesn't depend on theta, this C function over here. And this is it, folks. This is the generalized linear model. You just model the systematic part using a response function or a link function. So you model the mean as a function of a linear predictor for Jacob covariates. That's the way you model the mean. And then you model the variability of y around the mean using a univariate exponential family, which is just a distribution that has this specific expression. That's it. That's a generalized linear model. What we are going to do now is we are going to dive a little bit into this model and discover some properties of the model. And also we are going to see some examples of the model. So it's, as I said, it's a unified framework that allows us also to create a unified computational procedure to fit this family. And once you have a procedure to fit any model in the family, then you can use the same procedure for the linear regression, for the Poisson regression, for the logistic regression. So it's a very useful generalization. As I said before, we are going frequently to consider this as a function that depends on the psi and w. This psi is what we call the dispersion parameter, and w is typically as a weight. For instance, if you're dealing with individual data, like when you have, for instance, Bernoulli data, then typically w is equal to 1. If you're dealing with group data, for instance, while you're dealing with binomial data, then, for instance, if you use the mean as the response, then W is equal to the sample size. This is, for instance, what you do if you are going to have binomial data and you establish your heuristic model, not to model the Y, but to model the proportion. Then you consider just a specific W. It's just an element there that gives you generality, flexibility when you are dealing with different type of outcomes. Now, for the Bernoulli and the Poisson distributions, you have no dispersion parameters, in the sense that for the Bernoulli and Poisson distribution, we are going to see the details later on. This function, this A of size and W is equal to psi is equal to 1. You do not have a psi, or you have it equal to 1 if you want. So that's a characteristic of the Bernoulli and the Poisson when you don't have over dispersion. If you have over dispersion, we have to use this kind of quasi-likelihood approach. We're going today to see a little bit more detail in the detailed way about these quasi-likelihood models. But in general, if you don't have over dispersion, Bernoulli and Poisson have psi equal to 1. For the normal distribution, the dispersion parameter, this function A of psi W is equal to psi. The dispersion parameter is, as you can expect, just the variance. That's what the variance in the normal model give you, the dispersion. So if you try to express a normal distribution as a univariate exponential family, what you will find out is that A of psi W is just psi, which is just sigma squared. And typically, when you're dealing with this univariate exponential family distributions, you are interested in theta, and this parameter, this dispersion parameter psi, is more like a nonsense parameter. If you remember, when you deal with linear regression, you are more interested in the mean, and then the sigma square, the variance of the model, is something you estimate because you need it to do inference, etc., but it's more like a nonsense parameter. And then finally, this C function here, as I said before, it will change depending on which specific model you're using, but the most important thing is that it doesn't depend on theta. Okay, the log likelihood. The log likelihood, well, you know, you have the likelihood, and then the log likelihood is the logarithm of the likelihood. If you apply it, let's assume that you have sample size 1 now, that you only have one observation, just to do a little bit of the math. If you calculate now the logarithm of a univariate exponential function, this is what you get. This is the logarithm of a univariate exponential function. Just take the previous general expression, calculate the logarithm, and you get that. Now, you know that this has to satisfy a property. If f is going to be f of y, theta is going to be a distribution, a density, then the integral has to be equal to 1. And if you calculate now the derivative, the first derivative of this equation over here with respect to theta, and then you calculate the second derivative with respect to theta, then you get these two identities here. So the expected value of the derivative of the log likelihood with respect to theta has to be equal to 0. And second, you have this other expression here, the expected value of the second derivative of the log likelihood with respect to theta plus the expected value of the derivative of the log likelihood with respect to theta squared. That sum has to be equal to 0. From where we get that? Well, it's very easy. Take this equation, calculate the derivative with respect to theta, both sides. Of course, the derivative of 1 with respect to theta is 0 because it's a constant, and you will get this equation over here. Calculate the second derivative, and you will get this equation over here. Now, why we are doing all this? Well, wait a minute, we're getting there. Just follow me for a second. Now, see, if you now take this expression here and you calculate the derivative of the log likelihood with respect to theta, what do you get? Well, you get this expression over here. This is, if you want, what we use for the score equations, right? Score equations are based on these elements, the derivative of the log likelihood with respect to theta. And as you can see, it's just this part over here. The C function here disappears because it doesn't depend on theta. So you calculate the derivative, it just disappears. So what you have here, if you want, is the fundamental element of the score function. You get this. And if you calculate now the second derivative, that's what we use for the Hessian, the second derivative of the log likelihood with respect to theta, you get this expression over here. So this is the first derivative of the log likelihood with respect to theta. Here you have the second derivative of the log likelihood with respect to theta. And if you now play with all these four identities, then you get a couple of very interesting equations. That's what we're going to show you in the next slide. Look at this. If you put together 1 and 3, what you get? You get that this equation over here has to be equal to 0. And what does that imply? That implies that the expected value of y is equal to the first derivative of b with respect to theta. So you remember this b function that I told you it is a very important function when we just analyze the exponential family. When we just analyze the exponential family, I told you this b function here is going to play a very important role. One is that it has to be chosen in such a way that this f has integral equal to 1, but it's going to be more important than that. Well, here you have this function b. You calculate the first derivative, and now you also understand, because we also asked when we were introducing the univariate exponential family, we asked this b function to have a first and second derivative. Now you see why. The first derivative of b will give you the expected value, the mean of y. And remember, that's what we modeled in the systematic part. So essentially in the systematic part, when you use your response function, you are modeling the first derivative of b with respect to theta. And if now you put together equations 2, 3, and 4, what you get is this equation over here. And if you work a little bit, what you get is that the variance of y now is the second derivative of b with respect to theta times this a function that depends on the dispersion parameter and these weights over here. Now, pay attention to this. The expected value of y is equal to the first derivative of b with respect to theta. That's the expected value. Now the variance of y is the second derivative of b with respect to theta, then times this function over here. Now this element over here is a function of the mean. Essentially, the first derivative, the mean, this is just mu, and what you have here, what you have over here, is essentially the derivative of mu with respect to theta, right? Because mu is the first derivative, and here you have the second, so it's the derivative of mu with respect to theta. So most of the time, this function over here, most of the time, this function over here depends on the mean. So you can see them that in generalized linear models, the variance is mostly, most of the cases, related to the mean times this function over here. Now, summarizing, this first derivative of b with respect to t is called mu, and then this v of mu that we are using over here really shows that there is a relationship between the variance and the mean in generalized linear models. For most of the example, the exception, the normal is an example. The normal is a univariate exponential family distribution, and the mean and the variance are independent. We are going to see that a little bit later. But generally, all the members of the exponential family have this relation, this variance mean relationship. And is a very typical characteristic of the univariate exponential family. Actually, we call the normal, but actually the normal distribution is not that normal if you look at it from the statistical point of view. For instance, within the elements of the univariate exponential family, is the normal the only one that have this characteristic that the mean and the variance are completely independent. But in most cases, it is not the case. Of course, the normal distribution is called the normal distribution. We saw it. Why? Because due to the central limit theorem, they realize heuristically you can show that many phenomena in nature follow this bell shape. But from the statistical properties, is not that normal, we could say. So this v function here that appears in the variance of y, this v function over here, and that shows that the variance and the mean are actually related, that function receives a special name. It's called the variance function, because it shows how the variance depends on the mean. That's why it's called the variance function. And by the way, we will see later on when we use quasi-likelihood, essentially what we are doing is specifying this variance function in a specific way. But we will go to that later. Okay, let me show you that some of these special cases that we studied already are indeed special cases of the univariate exponential family. For instance, suppose that you have a Bernoulli distribution. This is a Bernoulli distribution. You just have a random variable y that can take two different values, 0 and 1. That's it. And we know that you can describe the distribution of such a random variable using the Bernoulli distribution that is given over here. Right? The variable takes value 0 with probability 1 minus pi, and take value 1 with probability pi. That's the Bernoulli distribution. And we know that for the Bernoulli distribution, the expected value is a probability. That's why we had to use the logic link. And the variance of a Bernoulli random variable is just pi 1 minus pi. We know that from our first course of probability back in the day. Now, if you calculate the logarithm of the Bernoulli distribution, what you get? If you calculate the logarithm, you get this expression over here. Now, let me show you that this belongs to the exponential family. Well, for that, first notice that if you apply some basic properties of logarithms, you get this. And if you apply another basic property of logarithms, you get this. And this is it. Look at this and compare this expression with the one we saw over here. Let me show you. Compare this expression with the one we saw over here, right? This is also the logarithm of the density of the exponential family. And if you look at what we have over here, it really looks pretty much the same way. What is theta? Call theta the logarithm of the odds, because if you look at here, what we have here is the odds of an event. Right? We say that event happens if y is equal to 1. That's the odds. And theta is just the logarithm of the odds. This is just the logically. And so if you define the natural parameter in this way, and then the logarithm of 1 minus pi, you can rewrite it in this way as a function of theta. It's basic mathematics. So you can write this distribution in this way, which is just the classical univariate exponential family. That's it. So the Bernoulli distribution can be written as a special case of the univariate exponential family, where theta is, b of theta is given like here. This is b of theta. A of psi, the weight A of psi w is just equal to 1. This function c of y psi is equal to 0. The first derivative of b then is given here. That's going to be equal to pi. The second derivative of b is going to be equal to pi over 1 minus pi. It's a little bit of basic math. But what we have shown here is that actually the Bernoulli distribution is a special case of the univariate exponential family. What about the Poisson distribution? A little bit more of the same. Here you have the formula for the Poisson distribution. We have seen it already. It's the typical distribution that we use when we have a counting process. So y is a count take value 0, 1, 2, etc. Now the expected value for Poisson distribution is lambda. It's the parameter we have over here in the equation, is lambda. And the variance of the Poisson distribution is again lambda. So the variance is equal to the mean. And if you calculate the logarithm of the Poisson distribution, this is what you get. And now it's very easy to see that this is a special case of the exponential family. Just choose theta as the logarithm of lambda. Choose that as a natural parameter. And then you can see very easily that you can write the Poisson distribution in this way, which is the general shape of the univariate exponential family. You just have to choose b of theta as the exponential of theta, which is in this case equal to lambda, because we choose theta equal to the logarithm of lambda. And then you can see very easy, choose that a function, forget about the w, a of psi comma w is equal to psi, that is equal to 1. Then this c function over here now is here, is minus the logarithm of the factorial of y, and you can see b of theta is the exponential, so the first derivative is equal to the second derivative is equal to the exponential and is equal to lambda. So you indeed have that this satisfies that the expected value is equal to the variance. So again, the Poisson distribution is a special case of the univariate exponential family. And then the other example that we saw was the normal distribution. Is the normal distribution a special case of the univariate exponential family? Yes, it is. So here you have the formula of the exponential of the normal distribution. And we know that the normal distribution has two different parameters for the mean and the variance. We have mu for the mean, sigma squared for the variance. Now you can calculate the logarithm of a normal distribution over here and you get this expression. It's the most complicated one. But this is, again, you can rewrite this as a univariate exponential distribution. Just choose the natural parameter equal to the mean. Choose this function a of psi w equal to psi equal to sigma squared. And then choose b of theta is as mu squared divided by 2. And remember that mu is equal to theta, so it's theta squared divided by 2. And choose this c function in this specific way. And you can see it depends on psi, because sigma squared is equal to psi, but it doesn't depend on theta. This part of here doesn't depend on mu, right? So that's it. Now you can write the normal distribution in this way over here, and this is just the general shape of exponential function. Just the first derivative of theta, here is theta. The first derivative theta is equal to mu, as you could expect, and the second derivative of b of theta. So this is theta, here is b. The first derivative is equal to mu. The second derivative of b is equal to 1, and then the variance is equal to psi times the second derivative, and psi is equal to sigma squared. The second derivative is 1. It's just a little bit of basic math, but the normal distribution is also a member, special member of the univariate exponential family. So it's a very flexible family of distributions that allow you to account for discrete distributions, like for instance the Poisson, of the Bernoulli, of the binomial, but also continuous distribution like the normal, the gamma, that we are going to see later on. Okay, here you have some special members of the exponential family. Here you have the general formula for the density of an exponential family. It is given over here. This is the general expression for a univariate exponential family. And you can see that the normal, for instance, is a special case of the family. Just choose theta, the canonical parameter, equal to the mean. Choose b of theta as theta squared divided by 2, and choose the psi equal to the variance. And you get a binomial. If you have the Poisson, for instance, it's another special case. Just choose theta equal to the logarithm of lambda. Choose b of theta as the exponential of theta, and choose psi equal to 1, and you will get the binomial. And the same, you can get the gamma distribution, you can get the inverse Gaussian distribution as a member of the exponential family, etc. So there are many, many known distributions that belong to the univariate exponential family. Now, take into account that the above list of the exponential family members is not exhaustive. There are other members that I didn't put in that table. For instance, the negative binomial distribution belongs to the exponential family. So when we were dealing with Poisson data and we're using the negative binomial model, that's a generalized linear model, because the negative binomial model, the negative binomial distribution, is a special member of the univariate exponential family. The geometric distribution is a special case as well, because it's a special case of the negative binomial when you choose k equal to 1. So the geometric distribution is also a member of the univariate exponential family. And it's not that all distributions are in the family. For instance, a very well-known distribution, the Weibull distribution, something we use a lot when we try to model time to event data. So time to recovery, time until certain components stop working. We use frequently in that type of settings the Weibull distribution. And the Weibull distribution does not belong to the exponential family. So it contains many, many useful distributions, but there are also useful distributions that are not included in the exponential family, in the univariate exponential family. Okay, now let's write down our model. Let us now to go to the generalized linear model in a little bit more of a formal way. Now, suppose that you have the response variable yi. So this is now the response of subject I. Suppose that you have n subjects in your study, and the response of all these subjects are IID, independent and identically distributed. So yi has nothing to do with yj, right? And we are going to assume that each of these yi's come from a distribution which is a univariate exponential family distribution. So we are going to consider that yi's are distributed following this distribution. And as you can see here, the theta now depends on the individual, depend on the subject, right? And you can see that the weights over here may also depend on the subject. Now, the psi here does not depend on the subject. It's what we call a common dispersion parameter. So we have now a set of observations. We have response yi for individual I. These yi's can be binary data, survive yes or not, cure yes or not, whatever. It can be a Poisson data. You can have, for instance, the number of cases with certain conditions in certain hospitals in certain time frame, whatever. This yi, you have independent yi's that come from an exponential distribution, and the natural parameter may depend on the subject, and the weight may depend on the subject, but the common dispersion parameter, as the word itself says, is common. Now, the expected value of yi is just the mean of the distribution, called mu I, and we know that this is just the first derivative b evaluated in theta I. And the variance of yi, as we saw before, is just the variance function, is the second derivative of b with respect to theta. It's the variance function, which is related to the mean, and then just times this function a that depends on the dispersion and the weights. And as I said before, typically we consider this a function as a ratio between the dispersion parameter and these weights. Typically, that's the expression that we use. And when you have w equal to 1, wi equal to 1, you have ungroup data, like for instance, Bernoulli data. And when you have wi equal to 1 divided by ni, is when you use the response variable you're using is the sum of ni responses. We call that group data. For instance, that's the case when you're modeling binomial data. And when you use wi equal to ni, then the response is equal to the mean of these ni observations. That's, for instance, when you are using a logistic regression, but you with binomial data, but instead of modeling the response y, which is the sum, you're modeling the proportion. In that case, wi is equal to 1. So it's a very general, flexible model. Now, where my covariates enter? Well, what you do with the covariates, the systematic part, is you model now this mu I as a function of your linear predictor. Remember that this mu I is just the first derivative of B evaluated in theta I, and theta I is the canonical parameter here. So let's do that. So you have a vector of covariates, xi, that have p components. You have an intercept, and then you have p minus 1 covariates. And now you're going to connect that covariance with the mean function, with the mean of the distribution, mu I, using your linear predictor over here and using your response function. So now you model mu I as a function of your linear predictors over here. Or equivalently, if you want, you transform your mean using a link function, and now you connect that to your linear predictors over here. These are two ways of doing the same, if you want. It's two ways of writing down your model. You can transform the mean and then link it to your linear predictors, or you can transform your linear predictors and then link them to the mean, right? So this H, of course, is 1-to-1, 2 times differentiable response function, and the link function is then just the inverse of the response function. They are just two sides of the same coin. And then if you want to get a specific GLM model, essentially you need to do two things. You need to specify the link function, how you're going, or the response function, how you're going to model the mean as a function of the linear predictor. And the second thing you need to do is to specify which member of the exponential family you're going to use in the second step, when you're trying to model the variability of y around the mean. So you have the systematic part and you have the random part. Once you specify the response function of the link function, then you have the systematic part of the model. Once you select a member of the univariate exponential family distribution, you have the distribution part of the model. So you fully specify your model by giving the link function, or the response function is equivalent, and by selecting a member of the univariate exponential family to model the variability of y around the mean. That's it. Once you do this, you specify these two elements, you have a GLM model. Now, I told you that when we were introducing the linear model, the binary model, the Poisson model, we chose typically the identity link, the logic link, the logarithmic link, and we call that links the canonical or natural link. Why? Well, the canonical link is if you model your natural parameter, the theta I, directly, you equal it, the theta I, to the linear predictor. That, of course, implies you're using certain link function, because the link function is what links the mu with the theta I. Well, that link function that implies that you are modeling the theta as x transpose times beta, that's called the link function. For instance, in linear regression, the theta I is equal to the mean. So when you equal the theta I to the linear predictor, which link you're using? The identity link, because theta is equal to mu I, and that's called the identity link. For instance, in binary regression, you know that theta I is the logic of the mean. It's the logic of the mean, that is the logic of the probability. So when you equal the theta I to the linear predictor, you're actually using the logic link. And that's why the logic link is called the natural link or the canonical link. Because when you use the natural link or the canonical link, what you're doing is you are modeling the theta over here, the canonical parameter, directly as equal to the linear predictors. And that's why we call it the canonical link. It's the link that allows you to model theta directly equal to the linear predictors. If you're using the Poisson, for instance, you know that theta is just the logarithm of the mu, the logarithm of lambda. So when you equal theta to the linear predictor, essentially what you're doing is you're using the logarithm of lambda equal to the linear predictor. And that's why we call the logarithm the canonical or natural link. Now, you can use other links as well. For instance, if you're dealing with binary data and you use the probit link, then you are just modeling mu as, well, here you have the cumulative distribution function of a normal evaluated in the linear predictor. And that now is not anymore the canonical link, because this is not the link you use if you want to model theta as directly as equal to the linear predictor. For that, you need to use the logic. In that case, theta will be equal to this. In this case, theta will not be equal to this, or to the linear predictor. The same for Poisson data. You can, for instance, consider the mean equal to the linear predictor. If you do that, you need to be careful, because the betas need to be chosen in such a way that the mu stay positive. But sometimes you use it. And in that case, you will not be working with the canonical link. But that's the reason we use the term canonical link. Okay, here, well, this is something that we saw already. In some cases, the model, when you use GLM, you consider a certain constants. The model contains certain constants which does not require to have a regression coefficient. You don't need to estimate regression coefficient for that element in the model. And that's what is called an offset. And we discussed that already when we saw the Poisson model. So for instance, if you have yi, and yi is the number of subjects showing certain event with certain value for the covariance xi. So yi is the number of subjects that show an event with covariance equal to yi, and you assume that this yi follows a Poisson distribution with certain mean, then the mean is going to be equal to ni times lambda I. That's the average number of events in the ith class. And the ith class is all the individuals that have the covariance equal to Si. Now, this lambda I over here is what we call an event rate. It's the rate per person years, for instance, in that class. And sometimes you want to model the rate, not the mean. For instance, when we were studying this skin cancer problem, where we saw that there were a number of skin cancers in different cities and different age group, but the number of people in each of these category was different. So it's what we were saying, 2 cases in 1,000 is not the same as 2 cases in 1,000,000. So you want to model the rate. And what you do there is you model the rate then as a function of the linear predictors, where an I here is the total number of person years in this class. And then when you apply just the logarithm of mu I, what you get here is, you apply it here, in this expression, the logarithm of mu I, you get a logarithm of an I, and then your classical linear predictor. And this is called an offset because you don't have a coefficient here, and you don't want to estimate anything about it. You just do it to be able to model the rate instead of the mean. But we saw already that. Okay, we have our model. If you have, what we have done until now is we did exactly the same we were doing until this lecture. We define a systematic part of the model, and we define a distribution part of the model. What is the systematic part of the model? You model the mean, the average response, as a function of the linear predictors. But to do that, you need to link that mean to the linear predictor, and you do that using just the response function. So you model the mean as the response functions evaluated in the linear predictors. Or, completely equivalent, you transform the response, you transform the mean using the link function, and now you model this transform mean as equal to the linear predictors. And that's the systematic part of the model. Now you need to go to the distribution part of the model. What is the distribution part? You try to explain now how the responses move around the mean. And to do that, we use the univariate exponential family distribution, which is a very general family distribution that encompasses the normal, the Bernoulli, the binomial, the Poisson, the gamma, the negative binomial. It's a very general family. So the only thing you need to do to specify a model is you need to choose the link function or the response function, and you need to specify which element of the exponential family you're working with. Fine, now you have your model, and the second step is how can I estimate the parameters in my model? And we go back to these very first conceptual lectures about statistical inference. That's why we invest some time there before, because it comes back all the time. What you do, well, now I have a probabilistic model and I want to estimate the parameters. So you can start using all the machinery of maximum likelihood. So basically you calculate the value of the parameters that maximize the likelihood of the data. So you actually observe that data, so it should not be very weird data set. So this data should be rather likely. On another case, your experiment have delivered just a miracle. You have observed something that is very unlikely. Can that happen? Yes, it can, but is very rare. So it makes a lot of sense to estimate the parameters using those values that maximize the likelihood. And how you maximize the likelihood? Well, the likelihood, remember, is the probability of the data, of the density of the data. If the yi's are independent, then the likelihood is the product of the probability of every yi, of the product of the densities for every yi. It's very annoying to work with a product. So what we do to calculate the logarithm, because the logarithm makes a product the sum. Now we are not working anymore with the product, but with the sum of the individual likelihood for every observation, the distribution of every observation, or the probability of every observation. And basically what you do now is, this is a mathematical problem. What you need to do now is you need to maximize a mathematical function. And now you need to go to calculus, or again, you need to go to the first two lectures of statistical inference. How you maximize this function? You calculate the zero values of the score functions. What is the score function? That's mathematics. You calculate the derivative of this function with respect to the parameters, to the variable you want to maximize on, and you equal that to zero. And that is just the score function. And if you do this for the exponential family, this is what you get. This is the score functions for the exponential family. And if you look at this very carefully, it will give you already some hint about the quasi-likelihood methods. Because if you look at the score functions depends on the mean. You have mu I over here. The score functions depend on the mean. You have it here, and you have it here. And it depends on the variance, because this over here is the variance. So the score functions in generalized linear models, in GLM, the score functions, you have this exponential family, which is a general distribution family. But the score functions only depend on the first two moments. The score function only depends on the distribution using the mean and the variance. That's it. You don't need any other characteristic of the distribution to calculate the score functions. If you have the mean and you have the variance, then you can construct the score function. And this will hint you already about, if you remember correctly, what we were doing in quasi-likelihood, you need to specify the mean right, and then you kind of approximate the variance. So you try to guess the variance. But this is because the score function essentially only depends on the mean and the variance. And if you do a little bit of mathematics, then you can show that this part over here can be written in this way. What you have done is you have calculated this derivative over here. This part, this derivative over here. This denominator over here is just the variance. And when you calculate these derivatives over here, you get just the xi vector. And what you get here is the variance, is this part over here. And then you get, by the way, when you calculate the derivatives, you also get this h prime. This is the response function evaluating the linear predictors. And then this part comes over here. And essentially, you can show that the score functions can be written in a completely general way in this fashion. What you have here is the design matrix, is the X matrix that is a matrix with row Si equal to the transpose of the covariance of individual I. This D function, D matrix over here is a matrix that's a diagonal matrix, and in the ith element of the diagonal, you just have the derivative of the response function evaluated in the linear predictors. And this matrix over here is just the inverse of another diagonal matrix that has in the diagonal the variance. And if you go back now to linear regression, or you go back to the binomial logistic regression, or you go back to the Poisson regression, and you look at the score functions, you are going to realize that they all have exactly this structure. The only thing you need to do is to plug in the corresponding mean in the corresponding mean in the linear regression model. This is just equal to the linear predictor. In the logistic regression model, this is just the speed function, etc. But you plug in here the mean, you plug in here the D, you plug in here the sigma, and you will see that whether you are dealing with Poisson, logistic regression, linear model, whatever, the structure of the score functions is exactly the same. So as I said before, this mu is just the vector of mean, is the vector of expectation. So is mu I is equal just to the response function evaluated in the linear predictors. Now, you will see that the score function is what I already mentioned, that the score function depends on the distribution of y only through the first two moments. As you can look at this equation here, the score function only depends on mu here, mu is here, sigma, the variance here, and you have also mu here because this is essentially the derivative of the derivative of the response function. So it's somehow you have the betas also here. But the score functions only depends on the first two moments of the distribution. Only depends on mu and the variance. That's it. Not other characteristic of the distribution is necessary. And well, you can calculate also the feature information matrix. Is just again to calculate the second derivative of the low likelihood, or if you want, the first derivative of the score function. And you can see that the feature information matrix is given here, where W is this matrix over here based on D and sigma square. So it's a diagonal matrix that has these W elements here, and these W elements are just given over here. So that's it. We have the score functions, we have the feature information matrix. Now you just need to solve these score functions, and you can use then the feature information matrix to calculate inference if you want to do a score test or WAL test or all that. Now, how to solve the score function? The score function, in this case, to calculate the maximum likelihood estimator, you need to solve the score functions. And we know, we saw it again, back to the inference, to the two first lectures about inference, you can solve the score functions using or Newton-Raphson method, or you can use also Fisher scoring, which in this case, if you are using the canonical link, then the Fisher scoring boils down to something called iteratively weighted least square. What is that? What is iteratively weighted least square? Well, essentially, what you can show is that when you apply Fisher scoring to solve this problem, essentially what you're doing is it's like you can show that mathematically. It's like you're creating some pseudo data, and this pseudo data satisfy a linear model, and solving these equations is some way like using weighted least squares. But this is some kind of mathematical thing that was very important back in the day, because back in the day the computing power was very limited, and of course the weighted least squares, when you try to solve, for instance, in linear regression, you saw that the maximum likelihood estimator has a closed form. You has a function for the beta. So if you are able to represent this model as some kind of least square problem, then you can solve these equations just like you did in linear regression. You have a formula. You don't need to do this iteratively procedures like Newton-Raphson, etc. But if you use a canonical link, then you can show that Fisher scoring equals this iteratively weighted least square, which is just like solving the normal equations in a linear model. It's a mathematical thing. Now, the canonical link function. If you use the canonical link, then you can show mathematically that the low likelihood is always concave, so the maximum likelihood is always unique if it exists. So you will have a maximum, which is unique. Now, and also you have that the expected and observed information matrix coincides. You have these properties. This is what happens if you use the canonical link. The maximum likelihood, if it exists, is unique, and the Fisher information equals just minus the H, and that is computationally convenient. Now, in general, the Fisher information matrix that we derived before, in general, it doesn't necessarily has an inverse. Even when this x prime x has an inverse, in general, this function, this matrix over here may not have an inverse. And that implies that then you do not have, your algorithm will not converge. For instance, a typical example of that is when you're dealing with logistic regression and you have separability, right? When you have separability, then this W matrix here, which is essentially in the logistic regression ni times pi I times 1 minus pi I. If you have separability, this is the null matrix. This is equal to 0. And in that case, the Fisher information matrix, of course, will be almost equal to 0, and that means that it will not have an inverse. It will be almost equal to 0 matrix, and we're talking about matrices. So there you have an example in which you don't have a maximum likelihood, a finite maximum likelihood estimator. In logistic regression, when you have separability, of course, you can use this. First procedure that would always deliver a final estimate, but the maximum likelihood is not finite. Now, if you have that these metrics can be inverted and you use the canonical link, then you know that the maximum likelihood algorithm converges to a maximum. The canonical link, the maximum is unique. If you have a non-canonical link, then you may have multiple maximas, and you need to be a little bit more careful there that you choose really the global maximum. But if you work with the canonical limb and the feature information matrix can be inverted, then there is a maximum and it's unique. And then, well, once you have the maximum likelihood estimates and you have the feature information metrics, then you can apply all the technology, all the machinery of inferential statistics. So we know that in small samples, maximum likelihood estimators do not have any optimal properties, but if you go to asymptopia, if you go to the land of the big samples, then the maximum likelihood estimator is really the king, in the sense that it satisfies all these nice properties we saw in the first class, the first two classes. It is asymptotically unbiased. It is asymptotically efficient because it reaches the variance, it reaches the lower bound of the Cramer-Rao inequality. So it's the most precise estimator you can have. It is asymptotically normal, it's normally distributed, it is consistent. So in asymptopia, the maximum likelihood is your best choice. So the maximum likelihood will satisfy all these properties we saw before. Now, typically in regression, we do regression conditional on the covariance, so you assume that the covariance are fixed, that they are not moving. Now, of course, in practice, the covariance not always remain fixed. Sometimes the covariance are themselves random variables. So you're doing an epidemiological study and you're selecting a number of people in a population, and you are measuring for these people the response and covariance. Well, these covariance, of course, are themselves random. And in that case, of course, you need to make some extra assumptions. This is also in linear regression, in logistic regression, in all regression is the same. You can assume that the covariance are fixed, or that you are making inference conditional on the covariance, or you can assume that the covariance themselves are random. And in that case, for any practical reason, things stay pretty much the same. But you need to make this theoretical assumption over here that these converge in probability to 0, these metrics, and then the maximum likelihood estimator is asymptotically normal. The mean is the correct value of the parameters, and the variance covariance matrix is given over here. In practice, of course, you need to estimate these metrics. X is just the design matrix, contains the covariance. What you need to estimate is this W over here, and you just estimate it, plugging in the maximum likelihood here in the W. So you get this asymptotic distribution. If you don't use a canonical link, again, more conditions need to be satisfied. But essentially, you can now apply all the machinery of inferential statistics. When you have the maximum likelihood and you have the feature information, you can apply it all the machinery. Okay. In this way, we have now the estimator for beta, but what about the estimator for psi, for the dispersion parameters? Well, as I said before, typically what you do is, if you look at the score equations we saw before, you see that you had here, down in the score equations, you had, let me go back a second to show you, when you're dealing with the score equations, as you can see, you have the variance function, and then you have this A function that depends on psi and W. And well, you can see that basically you can calculate the maximum likelihood. We saw all that, but how can I estimate now the psi? Well, if you consider that the variance is just, well, the variance is always in this way, but now you write down A as the ratio between psi and W, which is typically what we do, then what you get is that the score equations can be written in this way. What you get is that the psi goes out of the equation. You get this out of the equation. And here you have the part of the equation, and this part depends on beta, but this element here doesn't depend on beta. So when you are going to calculate the maximum likely estimator for beta, so you're going to calculate the derivative. No, this is the derivative of the log likelihood with respect to beta. When you equal to 0, this disappear from the equation. You can multiply both sides of the equation by psi, and this essentially disappear. So you cannot estimate psi using the score equations. You cannot, because they just the psi disappear from the score equations. You multiply both sides by psi and the psi disappears. So you can use the score equations to estimate beta, but you cannot use the score equations to estimate psi. So how can we estimate the parameter psi? So as you can see here, the dispersion parameter disappears, and you cannot from the score equations, and consequently, this beta over here, the maximum likely estimator for beta, will not depend on psi. It's just size goes away, vanish from the equation. And in many practical situations, it's difficult to estimate this size using maximum likelihood, especially because, as you can see, it just vanished from the score equation. So typically what you do to estimate size is you use the method of moments. So you don't estimate the size using maximum likelihood, but you use the method of moment. Let's see a little bit in detail how this is done. Well, suppose that beta is known. Suppose that you have beta. Later we are going to handle that, but for the moment, suppose the beta is known. Well, you know that the variance of the response is equal to the variance function then times psi divided by wi, right? And what is the variance? The variance is the expected value. The variance of y is the expected value of y minus the mean. This is y over here. Don't get confused. This is mean, and then a square, right? That's per definition the variance of y. And that has to be equal to this part over here. So if you pass these two elements to the other side, what you get is this equation, right? You get an expected value of this term here inside is exactly equal to psi. And that's what we are going to use to estimate psi. So if you have now n observations and you sum, so you will have this equation now n times for every individual. If you sum both sides here over each individual, well, this is constant, it will stay n times psi that you divide by it and you get it here. So essentially, this is the expression you have. You have the expected value of this over here is equal to psi. So what the method of moments does is you estimate psi using just these statistics over here. And that's the way that size is estimated in practice. And as you can see, this part here is related to the Pearson residuals in GLM. So this is essentially the Pearson residuals we use in GLM. And this is the method of moment to estimate psi. And this is the way we estimate psi. If you remember, the same happens when you had linear regression. When you had linear regression, the maximum likelihood estimator, the normal equations, allow you to estimate beta, but you need to estimate the sigma square just using the method of moments. And here you see it in a completely general way. So we were assuming that you had beta, but we don't have beta. So you need to estimate beta, and once you estimate beta, you can estimate the mu, obviously, because the mu depends on the beta. So you need to take into account that, and that's the reason why we don't divide by n, but we divide by n minus p, where p is the number of parameters in your model, and now you plug here the estimator of the mean. And then you get a real estimator for size. And that is the typical estimator that we use for size. It's just a method of moments in which you estimate the betas, and that's it. And if you're dealing with the normal case, then you can show very easily that this estimator that we get here is actually just the classical S-square estimator that we get when we have the normal distribution. Okay, model selection, model fit. Well, you can now apply the same old machinery we saw before. If you want to compare to GLM in a completely general fashion, well, you can use the WALT test, you can use the score test, you can use the likelihood ratio test statistics. Just when we saw that in the first two lectures, these are completely general. The Holy Trinity is completely general. You can apply it here, you can apply it everywhere as far as you have a likelihood. If you have non-nested models, then of course you can use the AIC or you can use the BIC. All the things we study about model selection, this information theoretic approach and model selection, all these things will apply again here. Now, What about model checking, model fit? Well, again, you can apply the Pearson chi-square as we saw before. We can apply the Pearson chi-square. You can apply the deviance statistic. You can, if your model does have a psi, if you are dealing with the element, a generalized linear model that contains a dispersion parameters, then you can, the deviance will depend on these dispersion parameters. So typically you will work with the scale deviance. That will be the deviance divided by the scale parameters. That's if your model does contain a scale parameters. And well, you estimate the mu using here the deviance, of course, you have is the maximum likelihood ratio test comparing your model with a saturated model. So you estimate the mu over here using your model, and then this is the mean you get from the saturated model. It's the saturated model over here. And the scale deviance, of course, will not depend on psi because the deviance has a psi here. If you divide it by psi, then the scale deviance will not depend on psi. And then if Ni, you need to have group data, as always, if Ni is large enough and the number of parameters do not increase with the sample size, then you have, again, that if the model is correctly specified, then the scale chi-square, when you divide chi-square by the dispersion parameter, if you do have a dispersion parameter in your model, some cases you don't have it, then the scale chi-square and the scale deviance, they follow a chi-square with n minus p degrees of freedom. An alternative to that is, well, instead of using just a chi-square distribution, you can construct an F statistic in this way, and then this is going to follow, this is just the deviance under the null, the deviance under the alternative, the difference between the number of parameters, and this follows an S distribution with these degrees of freedom. And this is another way to test for goodness of fits. Notice again that if the sample size is small, if you don't have group data, for instance, when you are dealing like with the Bernoulli, then the chi-square and the deviance tests are not valid. They may not be the appropriate way to model or to account for misspecifications of the model to detect problems with the model. But you can also use the other residuals we saw in the previous lecture for the Poisson model. These residuals based on generating data under the model. You can always do that. So a rule of thumb that you can use is the scale deviance is going to be, if the model is correctly specified, the scale deviance is going to follow a chi-square distribution with these degrees of freedom. So if the model is correctly specified, then the scale deviance should be approximately, because this is the mean of the distribution, approximately n minus p. Just you can always have a look at it to get an idea if you may have misspecification on your model or not. Okay, until here, we have introduced the general model. We have seen some properties of the univariate exponential family. We have generalized all the models we have seen before. We have learned how to estimate the parameters using maximum likelihood. We have seen very briefly how to do model selection. We saw that very briefly because we devoted 2 lectures at the beginning of the course to study all that, the WALT test, the score test, the maximum likelihood test. So it's exactly the same. We don't need to put so much time on it. We also saw very briefly that you can use this information theoretic approach to model building. You can use the Akaike information criteria. Why we did that so briefly? Because we saw that in detail already as well. And it's just the same thing. And we also saw that you can use here, again, the chi-square test, which we have seen in Pearson chi-square test for goodness of fit. We have seen that many times. The deviance test of goodness of fit, we saw also already many times. The only difference is that now if you have a psi in your model, in the binomial data, psi is equal to 1. In the Poisson data, the dispersion parameter is equal to 1. But if you do have, like for instance, with a gamma model, you have a dispersion parameter, or in the normal case, you have a dispersion parameter that is not 1, then you need to work with the scale chi-square scale chi-square test. So you need to scale the deviance test to get a goodness of fit test. These tests, as we saw already, are valid when you have group data. If you don't have group data, you cannot interpret them very well. The same with the deviance residuals and the chi-square residuals. If you don't have group data, you can have a look at them, but it's very difficult to interpret it. And that's the reason why we introduced these other simulated residuals before as well. You can also use that residuals. So let's take now 5 minutes, and then we are going to see a very interesting sample of GLM. Okay, we continue. Now we are going to see all this machinery in action. We're going to analyze and study is the so-called Janka harness data. Is a data that has been used in different books and articles. The dependent variable here is the hardness of timber samples, the Janka hardness of timber samples. And it is believe that hardness is, well, hardness is a structure important, it's a quantity that they know that is closely related to the density of the timber. And what they want to study essentially is the relationship between the hardness and the density of this timber. The data comes from an old but interesting book from Williams, a book from 1959. And the author of the book, Williams, he works in a division of forest products. That's why he was busy studying this relationship between the hardness and the density of timbers. And he used this data for a very specific purpose. He used this data to give an example of a quadratic regression in the linear regression setting. And you may ask yourself, well, if it's a sample that was used to illustrate quadratic regression, what is the relationship with generalized linear models? But we will see that in a second. So here you have the reference for those of you that want to see the original data and the original application. So here we have the data set. It's called hard goods, and it counts. It has 36 observations, two variables. You have the hardness and you have the density of these timbers. If you make a plot here, then you see you have here in the vertical axis the response, which is hardness, and of course you have density as the covariate here. Now look at this graph. Look at this plot, because there are a number of characteristics of features in this plot that immediately become evident. You see first that there is some kind of curvature in the relationship. If you look at it, you see that you have this kind of pattern. But you also see there is some kind of variance heterogeneity, because the variability here is not that big, but you see that the variability tends to increase when you increase the density. So it's obviously you have a problem of heteroscedasticity here, so the variance seems to increase with density. So we have here a non-linear relationship, because you clearly see that there is some kind of curvature in the relationship between hardness and density, but you also see that you have a problem of heteroscedasticity in this model. So if you try just to apply the classical approach to these problems, what you will do is you will fit a linear regression model, you will use the element function, you will use a quadratic polynomial in density to try to model hardness. And if you do that, this is what you get. And you can see here that when you have, for instance, you apply the summary function, you fit your model, you put it here, we call it this HW of linear, and you see very clearly when you apply the summary function that the coefficient of density here was non-significant. However, if you now apply the ANOVA function to the same object, you get here a highly significant p-value for density. So the coefficient table give you something that is not significant, the ANOVA tables give you something that is very significant. Why do we have such a difference? Is that a contradiction? Where we already saw that and I already explained it, so I leave it to you as a homework. But actually, there is not a contradiction there. Now, the second thing is that if you consider now a polynomial of degree 3, so you try to still make your polynomial a little bit more complicated, then you say a couple of interesting things. For instance, you see that the intercept term is not significant here. Let's look at the quadratic polynomial. You see that the intercept and density is not significant. Some users will claim that this is a powerful reason to remove them from the model. So I don't have a significant intercept. I don't have a significant linear term in density. I do have a highly significant term for the quadratic term. So I can just use a regression through the region. I just can delete the intercept and the density. We know that that goes against the principle of marginality. We have more than once argued against that. But an average user, somebody that doesn't have a kind of very deep insight in all these things, may find this a good reason to remove them. And if you apply kind of automatic model selection procedures, for instance, like a stepwise regression, they will find it difficult also to avoid removing these variables from the model. Now, we know that this is not a good idea, and we will still see once more why. The other thing you see is that the coefficients change widely if you go from the second to the third degree curve. You see it, for instance, in the coefficient of the quadratic term. In when you just have a degree 2 polynomial, that coefficient is positive. However, when you add the third degree term to the polynomial, then the coefficient becomes negative. So this is kind of a little bit of a weird thing, because you have this high variability when you add just the cubic term to your model. Now, the problem that, of course, we know it is a kind of problem of collinearity. When you are dealing with polynomials in linear regression, you get this problem very frequently. And a way of handling this problem is, well, you can use orthogonal polynomials, is what you get in R with the poly function, and then you solve that problem. Another, if you want more simple solution, is you just can sometimes center your covariate. So what we are doing here, what we are going to do here is we're creating now a new variable density, now with a small letter, not with capital letter, which is just a center version of the original density. We are just calculating the density minus the median of the density. And this is it. This solves many of the previous issues. You see, for instance, that you get now more stable results. So when you add a cubic term to your model, then the coefficient of the quadratic term doesn't vary so widely. Before it was going from positive to negative. Now it goes from 0.5 to 0.4, which is a much more stable result. The second interesting thing is that now the intercept and the linear term is highly significant in both models. So when you work with the uncentered variable, they were not significant. When you center the variable, they become highly significant. So the proponents of removing the intercept and slope before, when you had the center version of the covariate, and they even can claim that that was a reasonable thing to do from the nature of the problem, because you may argue, well, if I have zero density in the timber, then obviously I should have zero hardness, right? Because if the density of the timber is zero, then the hardness should be zero. Yes, that will support the idea of removing the intercept and the linear term and just to stay with the quadratic term. However, what is more difficult to explain is why the curve, if you just consider, if you remove the intercept and you remove the linear term, and you just consider the square of density, that has other implications. It's not only that that curve will pass through the region, that's true, and that's something that you may argue is logical, because if I have zero density, then I should have zero hardness. You can argue that. Okay, a model without intercept and density will indeed satisfy that property. So from that point of view, it makes sense, but that model will satisfy other property. That quadratic curve, that parabola, will pass through zero in a flat way. So the derivative in zero will be equal to zero. It will touch zero in a flat way. And why is that reasonable? I mean, just removing the intercept and the slope, it will impose extra conditions on how this curve have to be close to zero. And we do not have data close to zero. So we cannot check that this property that we imply with a quadratic term alone is actually correct. The problem is, if you remember when we studied the linear regression back some lectures back, the problem is that linear regression models many times are just approximations. They are never intended to have validity outside certain neighborhood of the data, outside the range of the data. So this model was always intended to be valid locally, and it has limited scope for extrapolation. You are now saying something about this model touches zero, and it's true that it should pass through zero, because if you have zero density, you indeed will have zero hardness, but that may pass through zero following a completely different shape that is not given by this quadratic model over here. So keep in mind that the model, and I showed you that using this Taylor expansion. If you remember when we were studying regression, I showed you that this Taylor expansion of a general regression model, and I told you linear regression models are frequently valid locally. So We do not have any value close to zero in the data. It's very difficult to say that this curve certainly will pass through zero, but maybe it's not even a quadratic polynomial. Maybe it's a much more complicated general function, and we just are approximating it using this quadratic polynomial because within the range of the data, this seems to be a good approximation. So it would be very difficult to argue that what actually happened at this point zero, because we do not have data there, except that we know that the curve should pass through zero. But which shape in which it should pass in a flat way as a quadratic term alone will imply? Probably not. So please just keep your intercept, keep your density, keep in mind that this model is meant to be valid only locally. And the second thing is, well, I told you that we got a lot more stability after centering the covariant over here. So here you have the model. So we fit our quadratic model. What you have, the blue lines are just the confidence bands for the mean. And well, that was the original application this Williams used with this data. He just wanted to show a good example of a polynomial degree 2 linear regression. Now, if you plot now the residuals for this model, this is what you get. So you get this megaphone type of pattern. And this is clearly a problem because linear regression, you should have the homoscedasticity, you have the homoscedasticity assumption, and it is clear that this assumption is not satisfied here. Also, if you do a QQ plot, you see that there are clear deviation from the normality assumption over here. So yes, a quadratic model seems to be reasonable, but when you look at the assumptions, you see that it is misspecified. You really have problems with this model. So, for instance, if you use the Bush-Pagan test for a heteroscedasticity, you get a very significant p-value. So indeed, we have a problem with heteroscedasticity. And what can we do? What can we do then? Well, a quadratic regression seems to be an adequate degree polynomial because when we look at the plot of density against hardness, we saw indeed that there is some curvature. And well, the quadratic, if you look at the graph before, the quadratic model seems to capture that reasonably well. It's the red line over here. So yeah, a quadratic model seems to be a rational way to describe this curvature. But the plot of the residuals versus the fitted values makes evident that you have a problem with homoscedasticity. And when you look at the QQ plot, you see also that we have a problem with the normality assumption. There seems to be a problem with skewness. The tails of the distribution seems to be thicker than the tails of a normal distribution because we see basically this departure over here from the line. So it's a problem, it's a tail problem with the distribution. So yes, a quadratic model seems to describe the curvature, but the model seems to have several problems. No, you may think, well, maybe it's that we have some kind of outlier, because if you look at the residual plots over here, well, you see that there is some kind of outlier points over here. However, if you remove the outliers, the problem stays the same. And also, you can also show that when you test if these observations are actual outliers, you have problems to claim that they are outliers. So the problem is a little bit more, is deeper than just thinking that this was caused by an outlier. Now, what we are going to do now is we are going to do a box and plot transformation. That's typically what you do when you have this type of problems. But we are going to do a box and plot transformation for the linear model without including the quadratic term, and for the quadratic model. And let's see what we get. So here you have, this is the box and plot transformation for the linear model. Then it tells you that you need to transform your data using a root square, right? Because it's 0.46, 0. So the box and plot with a linear model tells you that you need to work not with y, but with the root square of y. That's what you get. So a root square will allows you to linearize the model. So you see that you have this quadratic, this curvilinear shape. If you want to solve that and to transform that into a linear shape, you need to work not with y, but with the root square of y. That's the conclusion of this box and plot analysis. However, if you work with the quadratic model, then you get another type of transformation. It's more like a kind of logarithmic transformation. Here you have the two graphs. So this is what you get when you use the linear model. The lambda should be around 0.5. Well, when you work with the quadratic model, you see that 0 is contained in the confidence interval. So this is a very interesting result. So the Box-Acon transformation, in this case, give you two different messages. When you apply it to the linear model, it turns out that you need to use something like a root square transformation to make the quadratic regression linear, to get rid of this curvature. But when you apply it to the quadratic model, it seems that you need to use some kind of log transformation to make the variance constant, to remove this skewness. So what can we conclude out of this? Well, the author of this paper, when I got this example, he consulted John Elder. John Elder is one of the greatest statisticians of the 20th century. He was actually the one that proposed generalized linear models. So John Elder is the father of generalized linear model. So the author of the paper was facing this kind of dilemma that we are seeing here. He said, well, if I apply Box and Cox to a linear model, Box and Cox said, well, you need a root square transformation. But if I apply Box and Cox to the quadratic model, so when you apply it to the linear model, Box and Cox said root square, and you solve the problem of the curvilinear problem. You linearize your model. But when applied on the quadratic model, so what you need here is a log transformation to make the variance stable. So he consulted with John Elder, and John Elder, he proposed a very ingenious idea. He said, well, what you need to do is you need to use a generalized linear model there. Don't use a linear model, use a generalized linear model. But now use a root square link to make the linear predictor linear in density. And you need to use a variance function which is proportional to the square of the mean. And this is, what is this? This is a gamma distribution. This is just a gamma distribution. So the thing is that what you need to do here is you need to use a root square link to link the mean with the linear predictor, and for the gamma distribution, you have this nice property that the variance is equal to the square of the mean. So let's go back to the gamma distribution for a second, and let me show you how this model is. So it's just a distribution in the exponential family, and you say that y follows a gamma distribution with parameters alpha and beta. If it has this density, just the gamma density, and with this parameterization, you have that the mean is equal to alpha divided by beta, and the variance has this expression. But we are not going to use that parameterization. We are going to use this parameterization over here that depends directly on the mean. So when this is also a gamma distribution, but now mu is the mean. So the expected value of y is equal to mu. And then this gamma over here that you have in this part of the equation, this gamma is just an scale parameter, which is always positive. By the way, a gamma distribution is a distribution that you use for positive random values, and is kind of an skew distribution. There are other parameterizations of the gamma, but we are going to work with the last one we saw. So properties of the gamma distribution is used to model positively skewed distributions. It's used to model things when your response is kind of like this, when you have this kind of skew distributions. And since the variance is equal to the variance of the distribution is the square of the mean divided by this scale parameter, so a gamma distribution actually assumes that you have a constant coefficient of variation. It's just the root square of 1 divided by the scale parameter. So these are properties of the gamma distribution. It's a member of the exponential family. You just do your little bit of math and you get there. The canonical link for a variant for the gamma distribution is just the inverse of the mean minus the inverse of the mean. That will give you the canonical link. So the canonical link will be to model the 1 divided by mu as equal to the linear predictor. You need to be careful because mu has to be positive and the linear predictors will not always be positive. So if you're going to use the canonical link, you need to use some kind of constraint you need to constrain the regression coefficients to guarantee that the mean is always positive. So something that people usually do when they work with the gamma distribution is they don't work then with the canonical link, but with the exponential link, because the mean has to be positive. So instead of using the canonical link, which does not guarantee that the mean will be positive, because this part doesn't need to be positive over here. What people do frequently is, instead of working with the canonical link, they use with this exponential link, because that guarantees that the mu over here is going to be always positive. You remove that problem. But now what John Eldredge suggested is, he suggested to use a root square link, and then to use a gamma distribution with a root square link. And the problem is that in the GLM function, you don't have the root square link. But that's no problem at all, because R is flexible enough. It allows you to write down your own link function. So here you have, we did it already before, and now you can model hardness as a linear function of density, but now using a gamma distribution with a square root link. And when you do that, these are the parameters estimates you get. And you see that both the intercept is highly significant, and you see that density is also highly significant. Now, the gamma distribution has a psi parameter, has these scale parameters. And as you can see here, is estimated as 0.0097. Now, I told you that if you want to evaluate the goodness of it, a rule of thumb is that you should compare these two terms, and they should be approximately equal. But now pay attention, because this is the on-scale deviance, and you need to compare the scale deviance to the degrees of freedom. So what you need to do is you need to divide the deviance by the scale parameter, because the gamma distribution does have a scale parameter. And you can see that when you divide that, then you get 33.83, and this is indeed very close to the degrees of freedom. So if you look at that, it seems that the model actually is fitting the data well. But you can also look at the residuals, or the simulated residuals we saw before, etc. Now, this is the fit you got with the quadratic linear regression model. And this is the fit you go with the gamma GLM model. And you may think, what is the difference? Well, the difference is very small, right? So when you use the gamma distribution with a root square link, you get the blue line. When you use the quadratic polynomial for the linear regression, you get the red line, and they are very, very similar. The difference comes in the variability across this mean, because the predictions of the gamma model will be virtually the same as of the one of the polynomial, because you see the two lines, the two curves are very close. The problem is, so do I gain something by using this more sophisticated GLM model, using this gamma distribution with the root square link? Does that bring some advantage? Well, the advantage is when you are assessing the error of the prediction, because the less dense timbers, they have a much tighter error bound when you use the gamma model that with the normal model. And the heavier timbers, they have a much wider bounds with the gamma model than with the regression model. And that's actually what you could expect, because here you see we have a lot of data, so we expect the error bands to be very close. Here we have less data, so we expect the error bands to be wider. And that's what we get with the gamma model, but we do not get that with the regression model. So that accounts naturally for this heteroscedasticity, this fact that the variability seems to increase with density. And that we can solve it with the gamma model, but not with the regression model, even though the average, the mean, the red curve and the blue curve are actually very close to each other. Now, let's have a look back again to the quasi-likelihood models. Now you will see that a lot of things that we saw before can be framed in a very rigorous framework. So what you do in the quasi-likelihood model is that you use some kind of different variance function. But when you use quasi-likely, well, what we saw is that sometimes the empirical variance does not correspond with the variance predicted by your model. It happens, for instance, very frequently in Poisson, because the Poisson distribution implies that the mean is equal to the variance. And what you observe frequently is that you have a problem of over dispersion. The variance seems to be larger than the mean, and the model says it should not, it should be the same. So sometimes the empirical variance does not correspond with the variance the model states. The empirical variance, for instance, can be larger than what the model predicts. We talk there about overdispersion, or it can be smaller than what the model predicts, and then we talk about underdispersion. That may happen most of the time with Poisson data or with binomial data. These are the two classical type of data where you have this problem of overdispersion and underdispersion. Both can happen, but overdispersion is typically more frequently observed than underdispersion. Now, we have dealt with this with the overdispersed Poisson model. And for instance, one of the possibilities is just to use a different model. You can use the negative binomial model, which is also a GLM model. But okay, the negative binomial model allows for a variance that is different from the mean, so it may solve the problems. We saw in the previous lecture that in the case study of the papers published by the PhD students of biochemistry, we saw that the negative binomial model was actually the best model. But again, the negative binomial model is a full parametric model, and you may have situations in which you have overdispersions, you fit your negative binomial model, but it doesn't solve the problem. So it may be also not appropriate. It's a fully parametric model, and it may not be appropriate as well. And it may also be the case that you don't have a clear idea about the distribution of the data, but you do have an idea about the mean and the relationship between the mean and the variance. But more than that, you don't know exactly what is the distribution of the data. That may be also a situation in which you have information that allows you to specify the mean. You have some idea about how the mean and the variance relate. You can see that, like, for instance, in this timber data set that we saw, hardness and density, you can see that, you look at the graph and you say, well, there is some kind of curvature. You have an idea about the mean. Well, I say that there is a relation between the mean and the variance. That I know that they have like this mega foam pattern in the residuals, and that frequently implies some kind of quadratic relationship between the mean and the variance. But I don't know exactly what is the distribution. Here, Nelder, with this vision that he had, he immediately realized that you're dealing here with some kind of gamma distribution. But sometimes you just don't know. You just know more or less how is the mean and the relationship with the value. And also sometimes you may just want to assess the effect of the covariance on the mean. And that's what you're interested in. The variance is kind of a noisome parameter. The sad distribution of the data really doesn't interest you so much. You just want to know if this set of covariates are having an impact on the mean, on the average of the response. That's it. And in that kind of cases is when you use this quasi-likelihood approach. And we saw it already in the Poisson, but I'm going now to go back to the theory to show you a little bit more how this works. Now, if you have a GLM model, you estimate the parameters using just the score function. And if you look at the score function, you see that the score function actually, they do not depend on the entire distribution. The score function depends on the variance of the response, depends on the mean of the response. That's it. So the only information of the distribution that the score functions use is the variance and the mean. That's everything you use in the score function. You don't use the kurtosis, you don't use the skewness, you don't use any other property to distribution. The score functions, which is what you use to estimate beta, only depends on mu and the variance. Now, when you use quasi-likelihood, that's what you do. You specify directly the variance function because the variance is depending on the mean, so you need to specify the mean. The variance depends on the mean, and then this function a. So what you do is you specify the variance function. Instead of typically in GLM, this variant over here emanates from the exponential family, right? You have your model, and the exponential family tells you this is the mean and this is the variance. Well, what you do in quasi-likely is you specify these two things apart. You specify a mean and you specify a variance function, and this combination that you're specifying, this mean and this variance function, may not come from the exponential family. This combination that you have chosen may be incompatible with the exponential family, but that's fine. So if you're using GLM, this emanates directly from the variant from the exponential family. If you're using quasi-likelihood, not necessarily. You specify yourself, and they may not come from the exponential family. So for the quasi-likelihood method, what you do is you replace this variant function over here with a function you normally, if you're in GLM, this variance function emanates from the exponential family. Now you're going to specify it yourself. So you replace the variance with your own variance. That's what you do when you're doing quasi-likelihood. Say user specify variant function. And now these score functions are maybe not coming from a real likelihood, right? Because if you're using GLM, there is a relationship between these two things. And now you're putting there whatever you want. So that may not be compatible with the exponential family, but that is fine. And we are going to see shortly why that is fine. So actually, these score functions may not come from a real likelihood. They may come from something that we call a quasi-likelihood. From there comes the name. You can write this likelihood over here, and you can show that, well, if you calculate the derivative of that with respect to beta, you get this score function. The problem is that this is not like a real likelihood. This is some kind of quasi-likelihood. And why is that the case? Because you are plugging in here your own mean and your own variance, and these things may not be compatible with the exponential family. And why you would do that? Well, all the reasons I explained before. You may fit the model, and the model, for instance, you may fit a Poisson model, and the model is not good. It's clearly misspecified. And you may say, well, you know what? I just want to estimate the effect of this covariance on the average count. And I'm not interested so much in what is the cycle distribution. If it is Poisson, negative binomial, or whatever else, I don't care. I just want to estimate the parameters. And for instance, in that case, you can try to solve the problem in this way. Now, so here you have the quasi-likelihood function. It's just the sum of all these quasi-likelihood, and it behaves kind of similar to a low likelihood, even though it is not a real likelihood. And as you see now, the score functions of this quasi-likelihood are exactly the score functions you had before when you plug in here your own variant function and here your own mean function, right? And the solution is found is you take these quasi-score equations to equal to 0, and you solve this equation. Now, this is exactly the same structure you get with the score function coming from maximum likelihood. The difference is that the variant function now is not derived from a statistical model. It's not derived from the, for instance, exponential family. It's something you're specifying yourself. So this type of equations over here, they are called quasi-score functions, quasi-likelihood. They are also called sometimes generalized estimating equations, GEE. And this is going to come back later, for instance, when you study longitudinal data. There's going to be a generalization of this quasi-likelihood approach. They are called quasi-score function, quasi-likelihood approach, generalized estimating equations. Okay, how do you work out this in practice? Well, you specify separately the mean and the variance. Now, this pair of mean and variance that you choose may not be compatible with the exponential family, but that's fine. It may not correspond to a proper likelihood, but with a quasi-likelihood. And you even don't need to get the variance function correct. You even don't need this variant function you're specifying may not be the correct variant function for the data. It's okay. We call that a working variance function. They don't even need to be correct. What you need to get right is the mean. That's what you need to get right. So if you get the mean structure right, so if you are sure that this is the correct response function and this is the correct linear predictor, you need to get that right. If you get everything wrong, you cannot make correct inferences. So this is already very general. You only need to get the mean right. But if you get the mean right, then the expected value of the quasi-score equations is going to be equal to 0. Why? Because the expected value of this part over here is going to be equal to 0. Why is going to be equal to 0? Because you got the mean right. So the mean of y is indeed this. So the expected value of the quasi-scores equations is going to be indeed 0. And then you know, and we saw that back in the inference first two lectures, how many times we have gone back to them. We saw maximum likelihood of specification and all these things, and I show you that the estimator that solves the score equations is going to converge to the beta that makes the expected value equal to 0. So you're going to, you got this right, then your estimator of beta emanating from this equation is going to converge to the true value of beta. You got this correct. The mean is correct. So you will get consistent quasi-likelihood estimator of beta. They are going to be consistent. They are going to approach the true value of beta. And that's everything. The rest of the equation is wrong. This part here is wrong, but you got this part right. And using these quasi-maximum likelihood estimators, then you can estimate the psi parameter as well, using the Pearson residuals of the deviant residuals that we saw in equation 22 when we use the method of moments to estimate sigma. You can use the same procedure now to estimate sigma, but plugging in not the maximum likelihood estimator of beta, but the quasi-likelihood estimator of beta. That's it. That's the quasi-likelihood procedure. So generally in GLM, you have this relationship. You know, the variance is equal to the variance function and then times this A function here. Let's see, for example, how you can handle over dispersion. For instance, when you have over or under dispersion. In that case, you can consider, for instance, the scale model. If you have Poisson data, you know that this is equal to 1. If you have Poisson data, the exponential family tells you that this has to be equal to 1. Here, you decide is equal to 1. Now, if you have over dispersion, then your model is wrong. Your data do not follow Poisson distribution. What you can do there is the following. You can say, well, I'm not going to work with the variance function implied by the Poisson model because my data is not Poisson. The mean and the variance are not equal. So I'm going to consider another variance function. For instance, I'm going to consider that the variance function is psi times this, the variance function, the working variance function that I'm going to use is going to be psi times V of mu. With this V of mu is the variance I got from the Poisson model. And this is called the scale model. And if psi is larger than 1, then you are accounting for over dispersion. If psi is smaller than 1, then you are accounting for under dispersion. And you can do exactly the same, for instance, if you have binomial data or if you have binary data. So this is the variance that you will get with binomial data. But sometimes you see that you have over dispersion, or in some rare cases, you see that you have under dispersion. Then you're not going to work, this will be the variance that emanates from GLM, from the binomial distribution. But the data is not binomial because the variance is not that, it's larger than that or smaller than that. So what you do is you plug in your score equations your own variance function. You just do size times the variance you get from the binomial model. And that will allow you to account for over dispersion. And the Poisson is the same. You know, the Poisson data implies that the variance is equal to the mean. But if you have over dispersion, then the data are not Poisson. And what can you do? You say, well, I'm not going to work with the variance that I get from the GLM model. I'm going to work with this working variance, which is going to be psi times lambda instead of lambda. And then you work with this working variance, you solve your quasi-likelihood score equations, and that's it. Okay, what are the properties of this quasi-likelihood estimator of the parameters? Well, you can calculate, well, here you have the quasi-likelihood estimator, the ones you obtained by solving the quasi-likelihood score functions. And how you solve these functions, again, you can use this, you can use the Newton-Raphson, you can use whatever numerical method you can you typically use to solve nonlinear equations. And then you can construct similarly, like you do in GLM, the quasi-Fisher information matrix, which is just given by here, which is the same matrix we saw before. And what you have here is that now this variance that appears in the W matrix over here are not the variance that you will get from a GLM model, but this will be these working variances that you defined before. And if you specify both things correct, if you specify the variance, the mean has to be correct. In another case, you will get into problems. But if you also specify the variance function correct, then you can show that the quasi-likelihood estimators are asymptotically normal with this mean, the correct value of the parameters. That's because you got the mean correct, and this variance for the quasi-likelihood estimator. But that implies that you got this variance function correct. Your working variance is the correct variance. Okay, but you told me that I don't need to get the variance correct, right? Yes, you don't need to. So if your variance is not correct, then you cannot work with this asymptotic result over here. You need to work with another asymptotic result. So if the variance function you use in your quasi-likelihood is not correct, if it is correct, you can use this result over here, this asymptotic result, to do your test, your confidence intervals, whatever you want. If the variance, the working variance you use in your quasi-likelihood approach is incorrect, then you need to work with the sandwich estimator. We saw also that, again, back to the two inference lectures at the beginning. So if the variance you use in your quasi-likelihood is more or less a roughly approximation, you are not sure that that variance is actually right, then you also have this kind of asymptotic normality for the quasi-likelihood estimator, but now you need to use the sandwich estimator. And this is something we also discussed back in the day when we were dealing with the inference lectures. Okay. The sandwich estimator, it gives you a consistent estimate of the true variance covariance metrics for your estimator. And even when you got this working variance wrong. So you can make valid inference for beta even if the working variance was wrong. The only thing you need to make sure is that you got the mean right. So the procedure is very general, is very flexible. You can get almost everything wrong and still you can make correct inference for beta, but the mean needs to be right. The sandwich estimator is also sometimes called the robust estimator because of the property we saw above. So it's a consistent estimate for the true covariance matrix, even when it was wrongly specified at the start. When you got this working covariance wrong, you still get a robust estimator for the variance covariance matrix of the quasi-likelihood estimator of beta. If you got the variance right, then the sandwich estimator becomes simpler. It becomes just what you would expect if you get the variance right. So even when the variance function is specified in an incorrect way, when this working variance is wrong, even in that setting, you can still obtain consistent and asymptotically normally distributed estimator for your regression coefficients using this quasi-likelihood approach. Okay? The problem is that, well, okay, if I get any way using this quasi-likelihood, you're telling that if I misspecify this working variance, I still get, quasi-likelihood estimators that are consistent and they are asymptotically unbiased and they are asymptotically normal. So why should I worry about getting the working variance right? Just specify whatever you want there and I still can do inference. Yes, that is conceptually correct. However, you may lose some kind of efficiency. So if you specify a working variant that is very far from the true, then typically you're going to lose efficiency. What it means is the standard errors you're going to get for your betas are going to be too large. So it's worthy to make some effort in trying to get this working variance as close to the true as possible. Use your brain a little bit. Don't specify there whatever you want, because yes, the results are going to be valid, but you may end up not rejecting any null because the standard errors are going to be very wide. So it's always a good strategy to try to get the working variance as close as possible to the true to try to minimize this kind of efficiency loss. Okay, let me show you now an example. We're going to devote the last part of the lecture just to see all this in action with an example. What we have here is the so-called teratology study, low iron teratology data. You have immersed rats that were put on an iron deficient diet, and they were divided into 4 groups. These groups received different number of injections to maintain their iron level. So you have group 1 that receives just a placebo injection. They were not receiving any supplementation of iron. You have a group 2, and these rats were receiving 1 injection at day 7 or 10. You have a group 3, and they were receiving 2 injections at day 0 and 7. And you got a group 4, and they were receiving 3 injections weekly for 3 weeks. So these are the 4 groups. Remember that their diet was deficient in iron. Now, these rats were pregnant, and they were all sacrificed 3 weeks after the 3 weeks. You start 3 weeks later in the experiment, they were all sacrificed. And for each of these animals, they counted the total number of fetuses, how many babies they had, that's called an I, and the number of fetuses, YI, that were the number of fetuses that were dead, and we call that YI. So that will be the response. So from all the fetuses a rat had, that's NI, rat I had NI fetuses, how many of them were dead, that's YI. And the hemoglobin levels of the rats were also recorded. This is kind of, I mean, it sounds a little bit, how I said, a little bit shocking the way these things are done, because they kill the animals and they were pregnant and all that. But well, this is the typical type of studies we do when we want to study chemical agents or dietary conditions on fetal development. And we need to do something like that, because of course we cannot do such an experiment with humans, and we need to learn sometimes. So it's a kind of typical design in this case. Now, suppose that you want to see the effect of group, and you want to see the effect of hemoglobin in this mortality for the fetuses. So this is a classical binomial setting in which you have you measure the number of success in a number of trials. Success here, please keep it in. Success is death, but I mean, just using statistical terminology. And so this is a classical GLM model for binomial data. So here you have the model. You specify that I want to model the number of dead fetuses as a function of the group and the hemoglobin level. And here you have your results. And well, you can see that, for instance, they consider group 4, that's the placebo group, if I remember correctly, the placebo group, yes. This is the group that have 1 injection, the group that have 2 injections, and the group that have 3 injections. So the control was the placebo, the reference was the placebo. And as you can see, where, for instance, you have here a negative coefficient. So that means that the number of death was smaller compared to the placebo group. That was highly significant. This is the same for when they got 3 injections, or when they got 2 injections, or when they got 3 injections. So you see clearly that these rats that were receiving this supplementation in iron with this injection, they had a less fetus mortalities. The fetus mortalities was smaller than in the placebo group. And if rather interesting, you see here, no, that's also expectable. The coefficient of hemoglobin was negative, and that means that also an increased hemoglobin has implies a less mortality for the fetuses. So that's what we get. Now, if you look at the deviance here, as I told you, a rule of thumb is that these two things should be approximately equal. And you see here a high difference between these two things. So probably we are having some kind of problem in this model. This is not fitting the data well. And if you apply, for instance, the simulated residuals analysis to check this goodness of it, you see, for instance, that the Kolmogorov-Smirnov test, remember that these residuals that are defined in this analysis, they should follow a uniform distribution. And it is clear that they don't. You reject that. And when you test also for dispersion, you also get a highly significant p-value here. So we have over dispersion in this model. And here you have, this is the observed value for the Pearson residual. This is the one you will get with the simulated data, and it is clear that we have a problem. We have a problem with this model. So a possibility is, well, if you seems to have overdispersion, then I just can use quasi-likelihood. Clearly, these data are not binomial. They don't come from a binomial distribution, because for a binomial distribution, the mean and the variance are strictly related. For a binomial distribution, the mean is n times pi, and the variance is exactly n times pi 1 minus pi, right? So, and we do not have this relation here. We have over dispersion. So what you can do is you can just fit the model using the quasi-binomial, the quasi-likelihood approach. And what you do here is you use this scale variance. The working variance now is going to be not the one you would expect from the binomial model, but psi times the variance you would expect from the binomial model. And of course, then this variance does not correspond with the variance of a binomial distribution, because the binomial distribution, this psi here should be exactly equal to 1. And it is not 1. So when you apply this model, then you get here, well, this is, again, highly significant here, was not highly significant in the other case. Yes, no, this is still the quasi-binomial. Let's have a look at here. Well, it was highly significant. When you use the quasi-binomial, the p-value was substantially larger, but still was very significant here. And as you can see, if you look at here, you get this psi parameter over here, and it should be 1 in the binomial model. And as you can see, it is not really 1. So the psi parameter here is almost 3, is far from the parameter, the value that is specified the binomial model. And as you can see here, the AIC is NA. That means why we get an NA there? Because this is not based on the likelihood. And you have to be also extremely careful when you look at the residual deviance and the null deviance and all that, because this is based on likelihood. And we are not using any likelihood approach. We are specifying a variance mean that we have to specify in the mean, and we are specifying the variance in such a way that that doesn't come from any likelihood. That's why we call it quasi-likelihood. So all these parameters here cannot be interpreted in a clear way. Now, there is another possible analysis for this type of data, for the so-called beta binomial model. And I'm going to show you this beta binomial now, because it's like the negative binomial for the count data. The beta binomial is a completely parametric model that is very useful when you have over dispersion, but now with binary data. The negative binomial is when you have over dispersion with Poisson data. So the beta binomial distribution is something you get when you have a finite sum of Bernoulli dependent variables whose probability parameter is itself random and follows a beta distribution. So you remember the binomial model is a sum of independent Bernoulli's variable, right? But they need to be independent. The beta binomial model is what you get when you sum Bernoulli variables that are dependent, and their probability, their individual probability, is itself random. So for the binomial model, you have independent Bernoulli variables x1, x2, xm. Each of these Bernoulli variables have the same probability of success pi, and then you calculate the sum. That sum follows a binomial distribution. The beta binomial distribution is what you get when you have now Bernoulli x1, x2, xn, but these Bernoulli random variables are not independent. You sum them, but now you're summing dependent Bernoulli variables, and they don't have a constant probability of success pi, but the probability is in itself random. So let's see this in a little bit more of detail. Assume that you have here a set of variables, yi go from 1 until m, and assume that conditional on P is the probability, they are independent Bernoulli, they follow independent Bernoulli distribution with parameter P. So if you have this is the probability, conditional on this probability, then all these random variables over here, they are independent and follow a Bernoulli distribution. Now, the next step is that we are going to assume that this P is a little bit the same as the negative binomial. You remember for the negative binomial, we assumed that the mean of the Poisson process was itself a random variable. Okay, and we are kind of doing the same. So this P probability now, we are going to assume that follows a distribution. It's a little bit like if we were in a Bayesian framework. Which distribution? Well, when you want to put a distribution on a probability, you typically use what we call the beta distribution. So we are going to assume that this P follows a beta distribution with parameters alpha 1 and alpha 2, which are positive. So yi follows a Bernoulli with probability P, and now this probability P follows a beta distribution with parameters alpha 1 and alpha 2. And here you have the equation of a beta distribution. And this is a typical type of distribution. When you want to put a distribution of a probability, you typically use a beta distribution. And well, what does that mean? Well, the expected value of this P, this probability, is going to be now mu, and this mu is given in this way, depends on alpha 1 and alpha 2, and the variance of this P is going to be given here, where mu is as before, but this rho parameter here is given in this way. And observe that this rho is actually positive because alpha 1 and alpha 2 are always positive. Now, what all this means? Well, marginally, what you're saying here now, because conditional on P, the y's are Bernoulli, right? That's what we said before. Now, marginally, what is the marginal distribution of the y's? So marginally, this y has mean mu is given over here. They have a variance which is similar to the variance of a Bernoulli distribution, because this mu is like a probability. So the variance is mu times 1 minus mu, but here comes the main difference. Now these Bernoulli variables are not independent. They have a correlation equal to rho. This is it. So if you now define the sum of these Bernoulli variables that have this mean, these specific means, this specific variance, but they are correlated, they are not uncorrelated. The sum of these Bernoulli variables, they follow a binomial distribution with parameters m and p, but now p is a random variable itself. And if you go back to the rat example, now you have a rat, and this rat had a number of fetuses. And for each of these fetuses, you have a Bernoulli variable. Dead, yes or not, right? And what you are doing in your model is you are counting for each rat how many fetuses were alive or were dead, equivalently. But now these Bernoulli events that you have within a rat, so you have for every rat a number of fetuses, and you're measuring alive or dead, yes or not, yes or not, yes or not, that Bernoulli events may not be independent because they are fetuses from the same mother. And that's why you probably got this problem in your model, that the model didn't fit, because the binomial model is it assumes that you have the sum of independent Bernoulli events. And in this specific case, these Bernoulli events probably are not independent because they are all babies of the same mother. They share some kind of genetic factors. They share, so they are likely not independent Bernoulli events. So here you have, what you have is this variable that conditional on P is binomial, but P itself is a beta. It's a random variable with a beta distribution. What is the marginal distribution of y? Then you need to integrate this binomial with respect to the beta for the P, and then you get this the marginal distribution for the y. So it's not binomial, it's beta binomial. So the marginal density corresponds to a variable y that has this specific form, and this is just the so-called beta binomial distribution. So you can reparameterize this model, this distribution in terms of mu and rho, and then what you will see is that the expected value of y is m times mu, like in the binomial case, but now the variance of y is m times mu, like in a binomial case, but you get this additional term over here. And this additional term is always positive because rho is positive. So it accounts for over dispersion. So you can get overdispersion in binomial data, for instance, when the binomial variable, the sum, is not the sum of independent Bernoulli events, but is the sum of dependent Bernoulli events. And in that case, a beta binomial model would be would be more appropriate than a binomial model. And okay, so you can interpret this beta binomial distribution as a binomial distribution with overdispersion. You have an overdispersion structure, and this overdispersion structure is characterized by this intraclass correlation over here. If the intraclass correlation is 0, then these Bernoulli events are 0. You are summing independent Bernoulli events, and in that case, your response variable y is going to be binomial. And you can see it very clear here that if rho is 0, this term disappears, and what you get the mean equal to m times mu, and the variance equal to m times mu 1 minus mu. That's a binomial distribution. So when rho is 0, you get indeed the binomial distribution, because then the y is the sum of independent Bernoulli. And the beta binomial is not in the natural exponential family. So it's not a GLM model, but it's a very useful model. Now the beta binomial model, how you specify the model? Well, suppose that you have this yi, like in the rat example, you have n rats, n can be whatever, it doesn't need to be rats, and it denotes the response variables, and we are going to assume that this yi follows this beta binomial distribution, and you can interpret this mu I just as a probability of a success for each of these dependent Bernoulli observations in cluster I. When you consider that the intracluster correlation is 0, you will be back to the binomial distribution. But in general, you will not consider that rho is equal to 0. And then what you do is you just use a logic link to link this mu, which is just the mean of this beta binomial variable, that is a probability essentially. You use the logic link to just link the mean with the linear predictors. You may also put a model on rho. You can also model this over dispersion parameter of this intercorrelation. You can model it as well, and then you can apply it again. Once you have a fully parametric model, you can go back to lecture 1 and 2, and you can apply all the machinery of inferential statistics. So you can now estimate the maximum likelihood estimator for beta, etc. So let's do this. So essentially, you can consider different models here. For instance, we are going to start with what we call the homogeneous phi, and that means that you use the beta bin function, beta binomial function in R. You specify the mean structure like before, so you want to model the number of dead fetuses as a function of group and hemoglobin. And here you put this random equal to 1, this factor here. What you're doing here is you're modeling this overdispersion parameter rho just as a constant. You're not modeling the intracluster correlation using covariates. When you do that, well, these are the results you get. So you get again a significant p-value. There is a significant difference between one injection and placebo. Here you have, there is a significant difference between these 2 injections and placebo. Here you have, and however, here now, this with the 3 injections, it was not significantly different from placebo. So apparently, if you overdo it a little bit, you don't get any effect. And also the effect of hemoglobin, you see again that it was not significant here. And here you have the estimate for the intracluster correlation. Here you have this value, and here you have the p-value was highly significant for that. Another thing that you can do is you can also try to model this intracluster correlation using group. You can see if this intracluster correlation, this overdispersion parameter, because it's the same interpretation, if it depends on the group. And if you do this analysis, these are the results you get. Well, they are very similar to the ones we got before, but you can see, well, this was really not significant, as you can see. So here you have. Let us now just to put the results of all the models together. So here you have the binomial model. These are the estimates you got with the binomial model. And here you got the binomial model when you use the sandwich estimator. They are exactly the same estimator, because the sandwich estimator, you just get the maximum likelihood estimators, but you just correct the variance covariance matrix using the sandwich estimator. Is exactly the same. Here you have the quasi likelihood approach that got exactly the same estimators. Think about why is that the case. And here you have the estimator from the negative binomial model. They are similar, but they are a little bit different. And here you have the standard errors you get for these parameters with the binomial model, that you see that they tend to be, generally speaking, too small, right? But you know that this is because the model is misspecified. These are then the standard errors you get, the binomial model, they tend to be smaller. And here you have the ones you got with the sandwich estimator, the quasi-likelihood, and the negative binomial. And they are kind of similar, not completely, but they are clearly larger than the one you get with the binomial model, which is, by the way, a misspecified model. So the standard errors you get from the sandwich quasi likelihood and negative binomial, they tend to be wider. They tend to take more uncertainty into account. Whereas the binomial model, they give you this very narrow standard errors, but it's essentially a result of the misspecification of the model. And okay, ladies and gentlemen, we have arrived to the end of the course. I hope it was interesting for you, that it was useful for you. And I'm really looking forward to see how you apply all these in your projects. So I wish you a lot of success in GLM and in all the courses you still have to take in our program. And well, we will see each other around. I will see you again in the exam. And if you have any question or any suggestion or whatever, please let me know via email. Success.